Assalamu alaikum wa rahmatullahi wa barakatuh. This is the second part of Chapter 9 Self-Induction. At the end of this chapter, we will be able to give the expression of the self-induced electromotive force and write the expression of the potential difference across a coil. Let's remember first, self-induction is defined as the phenomenon in which a change in electric current in a circuit produces an induced electromotive force in the same circuit. The coil has the tendency to delay either the growth or the decay of the current. The phenomenon of self-induction appears only in circuits containing coils traversed by a variable current. A coil traversed by a current I has a self-flux phi such that phi or flux equal Li. In order to obtain the expression of self-induced electromotive force, let's use Faraday's law. A coil of inductance L and traversed by a current I is the seed of self-induced EMF E, such that E equal minus d flux over dt. Since flux equal Li, so E equal minus d Li over dt. For a coil without soft iron core, L is constant, so E equal minus L di over dt. In SI units, E in volt, I in ampere, L in Henry, and T in seconds. Note, since L is positive, E and di over dt have always opposite signs. Now let's apply Ohm's law across a coil in order to obtain the expression of the potential difference. Consider a coil of inductance L and resistance R, traversed by a variable current and oriented positively from A to B. The potential difference across the terminal of this coil can be expressed as follows. U coil, which is equal to UAB, equal to Ri minus E, equal to Ri plus LdI over dt, since E equal to minus LdI over dt. This is the expression of the potential difference across a coil. Now in the steady state, the current is constant, then di over dt equal to 0 and UAB equal to Ri. So in this case, the coil acts as a resistor of resistance R. If the coil has no internal resistance, then R equals 0. So in this case, UAB will be equal to 0 and the coil acts as a connecting wire. Now in order to know the role of the coil in a certain circuit, we must take a look at E.I. Suppose that a coil is traversed by a current I and oriented positively from A to B, so in this case I is positive. If I increases with time, then di over dt, or the slope, is positive. So in this case E will be negative, since E equal to minus L di over dt. And so the multiplication of E.I will be negative. In this case, the coil acts as a receiver. If I decreases with time, then di over dt will be negative, and so in this case E will be positive. And E.I in this case will be positive, so the coil acts as a generator. While if I is constant with time, then di over dt equals 0, and so E equal to 0. In this case, the coil acts as a pure resistor. Let's solve application 2. A coil of inductance L equals 0.2 Henry and an internal resistance R equal 2 ohm is traversed by a current of variable intensity of expression I equal to t minus 1 in time interval t between 0 and 1 second. Part 1. Calculate the self-induced electromotive force that appears in the coil. I equal 2t minus 1, then di over dt equal 2 amperes per second. Since E equal minus L di over dt, so it will be equal to minus 0.2 multiplied by 2, which is equal to minus 0.4 volt. Part 2. Calculate the voltage UL across the terminals of the coil at instant t equal 1 second. U coil, according to Ohm's law across a coil, equal to Ri plus LdI over dt. We substitute the expression of I, which is equal to 2t minus 1, and we replace instead of t the value 1 seconds, so it will be equal to 2 multiplied by 2 times 1 second minus 1 plus 0.2, which is equal to the value of L multiplied by 2, which is equal to di over dt. The answer will be 2.4 volts. Part 3. Deduce the rule of the coil in the circuit for t between 0 and 1 seconds. Since I equal 2t minus 1 and E equal minus 0.4 volt, for t less than 0.5 seconds, I will be negative. So E dot I positive, and in this case the coil acts as a generator. While between 0.5 and 1 seconds, I is positive. So E dot I less than 0, and in this case the coil acts as a receiver. Let's now solve application 3. A purely inductive coil without an iron core of inductance L equal to 100 mH is traversed by a variable current of intensity I as shown in the adjacent figure. Purely inductive coil means it has no internal resistance. Part 1. What physical phenomenon is shown in this experiment? Of course, the answer is self-induction, since the variation of the current inside the circuit causes a variation in self-flux and hence creates an induced current. Part 2. Indicate with justification the time interval in which this phenomenon exists. For t between 0 and 10 milliseconds and t between 30 milliseconds and 50 milliseconds. Since in these intervals I varies, so flux varies, and since E equal minus d flux over dt, so E different from 0, and so self-induction exists. Part 3. Calculate the values of E in the preceding intervals of time. Since E equal minus d flux over dt equal to minus LdI over dt, for first interval between 0 and 10 milliseconds, di over dt is the slope, which is equal to 0.2 over 10 times 10 to the power minus 3 equal to 20 ampere per second. And so E equal minus LdI over dt equal minus 0.2 times 20 equal minus 4 volt. For the third interval, t between 30 and 50 milliseconds, the slope will be equal to minus 10 ampere per second, so E will be equal to minus 2 volt. Part 4. Indicate with explanation the rule of the coil in each interval. For t between 0 and 10 milliseconds, E equal minus 4 volt, less than 0, and I greater than 0, so E dot I negative. In this case, the coil acts as a receiver. In the second interval, E equal to 0 since I is constant and di over dt is 0, so the coil acts as a wire since it has no internal resistance. In the third interval, E equal 2 volt is positive and I also positive, so E dot I is positive and the coil acts in this case as a generator. Part 5. A soft iron core is introduced inside the coil. Interpret its effect on the inductance of the coil. As we know, the soft iron core increases the inductance of the coil. Now, as a summary, a coil of inductance L and traversed by a current I is the seat of self-induced EMF, E equal to minus L di over dt. The potential difference across the terminals of the coil of inductance L and resistance R is U coil equal Ri plus LdI over dt. If E dot I negative, in this case the coil acts as a receiver. If E dot I positive, in this case the coil acts as a generator. If I is constant with time, then di over dt equal to 0, so E equal to 0. In this case, coil acts as a pure resistance or as a connecting wire if it has no internal resistance. This is the end of part 2. Thank you for your listening.